Hello and welcome to Beamer Folk. After many years of good service, our quartz alarm clock decided to bite the dust, and instead of just ditching it, my curiosity got the better of me and I pulled out of it the little quartz printed circuit board as you see before you. This clock, there are many of these little clock modules that you can get from a well-known auction site, but this little printed circuit board seemed to be a cut above those, and so I thought I could build a precision instrument of sorts out of it. I wasn't quite sure what precision instrument, and I've chosen a particular one. But this little board, of course, drives a simple stepping motor, a minuscule little gear with a magnet in the bottom to spin it around. And that drives a continuous handled display in the alarm clock. There's no escape movement. This doesn't tick. This is continuous. Please follow me on my journey here as to how I applied this printed circuit board. If you're curious about how these clock mechanisms function and work, I can direct you through to a video from Diodes Gone Wild on YouTube. It's a video clip, and I'll put a link up here to that. I would like to invite you back to me again for two reasons. One is I apply this board in a precision way to a device, and secondly I've got additional information how this particular printed circuit board out of our quartz alarm clock differs from the one that Diodes Gone Wild did. And there are many of those modules, and this offers, from what I can see, a superior performance. But anyway, you're welcome to go and see that video. It's an excellent video, and there was no point in me doing it because he did it so well. Welcome back. I hope you enjoyed that. I know I did, and it gave you a grounding as to how this works. But going back to this printed circuit board here, the advantage, as far as I could see, demonstrated with this board is that Diodes Gone Wild clock module only lasted 2 months because its current was, I think, 1.5 milliamps, was it? Yeah, 1.5 milliamps. This little board only consumes 0.21 milliamps, that's 210 microamps. So that this little board on one AA cell would last for about a year, a great improvement over that. And I think this is mainly due to this coil. The coil DC resistance, I wasn't able to measure its inductance, and I'll tell you why in a minute, but this coil's DC resistance was 3000 ohms. It's actually a lovely little coil, and I hoped to recover it, but alas, by the time I'd carefully removed it, and if you come across one of these boards and you want this coil, be very careful how you removed it. I flexed it very slightly, and the wire is of extraordinarily thin gauge. I'm afraid it snapped, so it became useless to me. But I'm hoping at some stage to repair it, because I suspect it's probably something around 0.5 to maybe 1.5 Henry. So that is quite an expensive little choke if you wanted to go and buy it. Its inductance value would increase by inserting what was originally in place, the metal core. But unfortunately, the metal core in this got damaged, and I had to remove it and basically dispose of it. But I really wanted to reclaim this coil, but alas, I'm afraid I damaged it. The little sounder here, which I was hoping again to recover, was actually faulty. That was of no use to me. But nevertheless, I pressed on because I was in belief that I can still build something out of this. I go on to the next slide now, which is there. And this is the underside of the board, of course. And you've got a chip on board little circuit in here. I don't think it's a microcomputer or controller. I think it's simply a divider chain, an oscillator with a divider chain. And the coil terminals are here, and you've got a positive point here. I've indicated it with a red marker. You've got a positive 1.5 volts. This is an extremely low voltage, and the negative goes onto this terminal here. This is negative across here, but this is some form of switch. There's a contact in there, and I disabled that. So I move on to the next. This little strip here was probably used for testing. So I move on to the next clip, which is here. And this is the component side, of course, and you've got the little quartz crystal here, which I measured as 32 kilohertz. It's a fairly standard one, but this seems to be very stable in precision from what I can see of it. And you can see how I've attempted to remove the coil and found it to be defective, remove the sounder, put 2 wires to both lands where the coil used to be. I put these yellow wires in there. That gives me 2 outputs. One's effectively phase 1 and the other one's effectively phase 2. And that's about it for this. Let me move on to, oh yes, in fact, there's the power supply leads, plus or minus to our 1.5 volt source. Move on to the next clip, and you can see how I've wired these onto the board with the negative at that point there and the positive at that point there, which incidentally tracks through to this point here, which I've indicated with a red marker. And there's the chip on board, and I'll move on to the next slide. You can see how I've wired it up so I can connect this to a prototyping breadboard. Move to the next clip. Well, these are the 2 phases, which if you saw the Diodes Gone Wild video, you'll recognize these 2 outputs. There is a slight difference with this. The frequency is 8 Hertz, which is 0.125 milliseconds repetition rate. In the graticule, it's 10 milliseconds per graticule. So you've got here 10, 20, 30, 32 for the phase 1 pulse, and then blank to the next 0.125 period. And you can see phase 2 here, which is at 10, 20, 30, 40, 50, 60, 64 milliseconds from the beginning of this phase. The second phase starts, runs for 10, 20, 32 milliseconds, and then drops down again, and then will repeat on the next 125 milliseconds. So that's the 2 independent outputs. For my precision device, I've just used one of them. That's all I needed to use. And on the next slide, this is the trace across the coil, and you've got 32 milliseconds on in a positive direction, a dead period of another 32 milliseconds, and then a negative going 32 milliseconds here. The whole of this gets repeated 8 times a second, therefore 8 Hertz. So what uses, what applications can this little board, this precision little board, be used for? I thought of a few, one of which is a frequency source. Well, it is a frequency source. I don't need to do anything with that, and it's probably a bit boring. You could make out of it a counter, and there are 1,001 uses of a counter, but again, that's rather digital, and I was looking for something a little analog, perhaps. So I thought of a precision ramp generator. It's a bit old school, but it can be applied to many uses, and it's a little unusual. You can use a ramp generator to build, say, a digital voltmeter, or perhaps a voltage controlled oscillator, those sort of things that synthesizers can use. Or you can build the scanning circuit, the X and Y drives for a CRT. All our old television sets used that type of ramp technology to drive CRT tubes, and a ramp can be used for that. You can use a precision ramp for some quite sophisticated pieces of equipment. And so I thought that is the little circuit that I would build around this and see how it performs. This is the circuit squig of my precision 1 second ramp generator. Basic time accuracy equals 0.00032%. That's not bad. We'll start from top left and work our way across. It's quite a simple diagram, but we'll start here at the top left. I've elected to use a 9-volt DC supply, and that's at that point there. That could be a battery, although I've used an external power supply. The total consumption of all of this circuit is around 7 milliamp. The first thing it does, it goes into the Schottky diode here, D1, and gets reduced down to about 8.75, but I've called it 8.7. And that goes off to the various points. At this point here, it goes via R2, which is a 2.2K resistor, into two silicon signal diodes, D3 and D4. This is behaving as a shunt regulator, and the reason being is that the clock module, which is here, mustn't have in excess of 1.5 volts DC, so it's a very low level, and two diodes at 0.75 of a volt will produce 1.5 volts. Brings us to the module, doesn't it? And there are very few wires to this. You've got the negative attachment here, and the positive attachment goes, as I said, to that point of the anode of D3. There are two outputs to this clock module, and I've only used one. You can use either. And that goes into a logic level translator here, which is Q1. Of course, switching between 0 and 1.5 volts is not what a 4015 wants to see. What it wants to see is approximately from 0 volts to the positive, which is the 8.7 volts DC. So whatever switches on the output of this clock module, you want translating up to a level that the 4015 is happy to see. Moving slightly back here, this is a power on reset. I used a 4015, which is a dual 4-stage static shift register. You could actually use dual D-type flip-flops. You could use JK flip-flops. You could have a chain of them, maybe 4 of them, etc. But I had this stock, and it was already on the breadboard, and I thought it was interesting to use. But it needs to be initially cleared, and that is achieved by this little circuit here. You've got a capacitor going up to the positive rail, and you've got this resistor diode paralleling circuit down to the negative, with the anode of D2 connected to this junction here. Well, what happens is when you power up, C2 effectively goes to a short circuit, as it were, lifting this pin here, which resets both of the dual 4-stage static shift registers. Of course, the second one I've not actually used here, but it effectively clears that line there. And after a short moment of time, of course, that capacitor charges up via R1 to effectively to 0 volts here, or the negative. So that capacitor is now charged completely with 8.7 volts. If you were to switch off again, the supply side, the positive side of C2, will fall effectively to 0 volts, or the negative, which will mean that the negative side of C2 will drop below, or I should move the arrow this way, will drop below by 8.7 volts, below the negative. That diode D2 catches that negative pulse and quickly discharges C2. A couple of points I failed to mention was that D1 is of course a reverse protection diode. And the second item, when I tried this clock module at anything other than 1.5 volts, I think I tried it at 1.9 volts, the timing went out and the chip started to play up. So the 1.5 volts DC on this module is actually quite critical. Okay, moving on. The basic setup of the 4015 is such that I don't use the second stage, I only use the first stage. And including this loop here, which is a small inverter of Q2, that forms a feedback system within the clock. And the tap that I've taken off here, which is the green wire here with an asterisk, green asterisk there, I've taken off at pin 10. This produces exactly 1 second. There are other timing points, and I'll come to that later, but for the purpose of this 1 second ramp generator, pin 10 on the first stage is the one you're after. And that goes, as I said, through to the feedback on the inverter and along here to this capacitor C6. Well, what that is doing is that it's resetting the integrator, and this is the integrator here. It's resetting the integrator every 1 second interval. And how that's achieved is that it turns on this transistor here, which is Q3, and it effectively shorts out this capacitor, which is a 1 microfarad here. And there is a protection system here, because the signal at this point here, the other side of the capacitor, is a differentiated signal. That is to say that there is a positive going pulse and a negative going pulse. Well, the positive going pulse operates the transistor to short the capacitor, but the negative going pulse could, under certain circumstances, depending on the transistor type, etc., although I've never seen this in practice, but it could damage Q3 if you didn't have D5 there. D5 effectively catches the negative going pulse, similar to the way D2 catched here. D5 catches the negative part of the differentiated signal at this point here. So this transistor here, Q3, effectively operates as a switch. It's not a brilliant switch, it's an imperfect switch. I could have used a FET there, which would have been better. I would have had to have selected a FET for fairly low gate voltages at this point here, bearing in mind that this op-amp is operating within 8.7 volts. So its plus or minus supply is what, 4.35 volts. And to get a FET to operate efficiently at that low voltage, you'd need to hunt through a lot of data sheets. So I simply used an inexpensive little transistor here to fulfill that function. Moving to the integrator itself, you've got effectively a capacitor between the negative input and the output. There is a resistive chain here, and that is that if you can imagine the capacitor not being there at DC, so effectively this op-amp would then be operating as an inverting amplifier based on the resistors, these two resistors here, that is two resistors, there are three resistors involved, isn't there? But R11 and R12 are seriesed up to produce, they're two 5.6 megohms, so you're looking at 11.2 megohms divided by R9, which is 470k, which produces a gain of, what, about 20. Ideally, an integrator shouldn't use these two resistors. But if you were to do that and you consider the DC configuration, you realize immediately without those two resistors in a DC situation that this op-amp would be operating in an open loop condition. And op-amps do not like being operated in open loop conditions. That explains why that resistor there, but unfortunately, because the effect of these two resistors is to create a slight non-linearity in the ramp itself. If you think of a ramp as a right-angled triangle, the hypotenuse needs to be as line-like as possible. You should be able to put a ruler against it and see no deviation. Those two resistors effectively disturb that line very slightly and make the hypotenuse of the right-angled triangle slightly convex, not concave, but convex. It bows slightly outwards. What you would seek to do is make those resistors as high as possible so that you get as near to the line as possible. But I had in stock, my upper limit of these resistors is 5.6 megohm. Its linearity is best as I can make it. You can, of course, improve upon that, but we won't go there. So R9 is effectively the point in which current is fed into the integrator and causes the ramp. Ignore R10 for a moment and let's put the positive input here down to 0 volts. And the ramp will go from, as you can see in the traces of my oscilloscope, will go from 0.1 of a volt through to 1 volt. Perhaps I should at this stage, before I go into the bias of this ramp, which is this circuit here, perhaps I should shift over to this simple little circuit here, which is a supply rail splitter. It effectively takes the 8.7 volts and divides it by 2, which comes out at 4.35 volts at this point here. Using an op-amp as a supply rail splitter is okay. It is not brilliant. You can actually purchase dedicated supply rail splitters, and ideally it would be better if you had effectively 2 PP3 batteries in series to generate a 0 point and a plus and minus supply. But that would of course mean that a supply rail becomes 18 volts. So I've used 1/2 of this dual op-amp as a supply rail splitter. I had to put a capacitor on the output simply because on the output here, which is these two green arrows here, one side is 0 volts, which is this point here, and the other point is the output. Under certain capacitive resistive loads conditions, I experience oscillations on the output, and that is primarily due to the supply rail splitter op-amp getting slightly upset. And the way that I cured that is by putting this 0.47 microfarad capacitor on the output down to the negative rail, and that stabilized everything. So it worked very nicely. But going back to the integrator op-amp here, and incidentally, if it comes to integration and differentiation, I'm not a maths master. I can feel my way around it and through it, but there are some brilliant explanations over the mathematics of integration and differentiation on the web, and I certainly couldn't compete with them. Going back to the positive input of this integrator here, if you were to take this down to 0, this ramp would go from 0.1 of a volt to a peak adjusted at 1 volts DC. The adjustment for that maximum peak voltage is at VR1 here. I've used a 10-turn potentiometer and I tweak it until I got a peak on the ramp of 1 volts DC. But when this transistor goes to discharging the capacitor, it doesn't discharge it to 0, it discharges it to 0.1, and that is simply because a transistor's VCE saturation voltage is not 0 at its collector, it is approximately 0.1 of a volt, and that 0.1 of a volt is reflected on the output here. So the ramp is not truly going from 0 volts to 1 volt, it's going from 0.1 to 1 volt. And how I eliminated that is to put the non-inverting input here through to a slight bias network here, and that is formed by R16 and R15, R16 being 10k, so you've got a slight negative bias on this point here, and that pushes down to 0 volts. So if you're not getting quite 0 volts, if you adjust, say, R15, which I have done, go to a 330 ohm or to a 470 to make the 0 truly 0. Ideally, you could probably put a pot in there and effectively trim the minimum voltage to 0 volts, and then you'd have to trim to get the maximum volts of 1 volt there. I used a reference here. It's no good just using resistive dividers, because as the voltage vary, the bias would vary. So it needs to be put enclosed in brackets, as it were. And I use the green diode here, which is D6, as a band gap reference. So effectively this is 0 volts, and at this point here is minus 2 volts. And from that band gap reference, I was able to derive the trim for maximum voltage and the trim for the little negative bias to achieve 0 volts on the output. Right, moving on to the timing conditions of the 4015. Before I do that, I think I need to explain R10. The reason why R10 is in there, if you were to, on this integrator, take both the inverting and non-inverting pins down to 0 volts, you would find that there is, at this point here on its output, a slight offset, particularly if that resistor were not there. If you just had a link to the positive input, you would find that there is a voltage offset. You can improve upon that voltage. You don't really ideally want a voltage offset there. It's a very small millivoltage offset, but it is there. And of course it is proportional to the gain that you set up under DC conditions. But if you include a resistor in the non-inverting input to the op-amp, and I adjusted this empirically, and what you do is you put a value in there which is approximately somewhere in the ballpark of the values of these resistors. So you're looking at quite a high resistive value. And incidentally, the reason why we can put these high value resistors around this op-amp is that you've got FET inputs on this input. If there were transistor inputs, the values of these resistors would be in the K range, not in the mega ohm range. But anyway, back to voltage offset. So I just kept on increasing the value of this resistor R10, in quite large steps, sort of 50k, 47k intervals, until I reached a point where the voltage offset was at a minimum. And if you were to increase it beyond that optimum level, you would find that the offset would drift. This was a positive offset, but it would drift towards a negative offset. So what you really want is to make this ramp 0. you really need the offset voltage to be at a minimum, and I achieved that via R10. So R10 is actually quite important, and that is before you start playing with the offset here to get rid of the 0.1 of a volt. So I thought I'd add that. That's the reason why R10 is there, and it's 1.5 mega. If you tried a different op amp here, you would find that your offset voltage is different, and you'd have to adjust R10, zero out the op amp, and adjust R10 till you got zero offset on its output. But there you are, enough of that. Moving on to timing, this whole ramp circuit is based on a precision 1 second. But within the 4015, you can elect to choose different timing intervals. And the way you achieve that is by taking this green wire here that has both the negative feedback within the clock loop and the resetting of the integrator. If you took this and moved it effectively to pin 5 of the first 4-stage static shift register, if you put it to pin 5, you would get a frequency of 4 Hertz. If you put it to pin 4, that would be 2 Hertz. If you put it to pin 3, which is here, you get an unusual 1.6 Hertz. I have actually experimented this and found this out through practice. It's not just calculation. I actually saw this. Now, if you were to continue into the not used section, so that is the second 4-stage static shift register, and go to pin 13, you end up with 0.8 Hertz and 12.72. Pin 11, you'd get 0.61, and pin 2 finally you'd get 0.53, not 0.5 Hertz. It would be nice if it had been 0.5, but it's not, it's 0.53. Okay, having said that, so that can be very simply done by just moving this green point here to the various pins, and that's the reason why I've included this green point, so that you can move it around and play with it and get different frequencies. If you were to do that, please bear in mind that the ramp would be upset because you've got a different timing interval on the integrator. So if you moved it, say, from pin 10 to 2 Hertz, which is pin 4, you've got twice the frequency. So this ramp would lift from 0 to 0.5 of a volt, not to 1 volt. To achieve 1 volt, you would have to either change this capacitor to a smaller value, say 0.5 microfarad, or you'd need to increase the value of this resistor to approximately 1 meg. So as you change the frequency of this to achieve a ramp from 0 to 1 volts, you effectively need to alter your resistive capacitive network around the integrator. And that's all I can say with it. You can also make a completely different set of frequencies. It's quite versatile, this is, by moving the link pin 15 to pin 10. Keep the, in fact, actually you move that around as well. But if you move pin 15 to pin 3 or 4 or 5, you would make a completely different set of frequencies on this for each one of those. I haven't listed those there, and in fact I haven't really worked out what they are yet, but that's something for me to explore later. But there are a number of other frequencies you can derive from this 4015. Quite remarkable, isn't it, really? But I like the idea of a precision 1 second ramp. To have a precision 1 second in electronics could be very useful for other applications as well. Well, I hope that I've explained it to a point that it's comprehensible, and I hope you enjoy that. Anyway, I'll get back to the bench now. I thought before we go and have a look on the bench using my inexpensive DSO, I thought I'd show you the performance with kind of grown-up instruments here. You can see that the ramp is as close as I can make it linear. The hypotenuse is line-like, and you can see that the basic accuracy here is 3.4 millionths of a second, which translates to 0.00034%. The DSO does not read this level of accuracy, and that's a reflection upon the DSO that you're about to see. Okay, so this is the layout on the bench. At this point here, this is the printed circuit board, a little clock module from a Quartz Alarm Clock. Breadboard system here, you've got the 4015 chip there and a TLC 272 there. The DSO, which is here, I'll give you a slightly better shot of that in a minute, and the power pack for the DSO and a line conditioner which is over here, which was the subject of another video, and I'll put a link to that here. So now I'll move into the DSO and see what it's reading. Let's turn off the light there, and there we are. We can see that this is the frequency as derived from the clock module and the divider circuit, and this is the square wave that is actually triggering the ramp generator, and you can see here the frequency is 1.026 hertz, and as I said, that 026 error here is more to do with the DSO than it is to do with the circuit. And there we are. And what I'll do now is I'll wire this up to the ramp so you can see the ramp in operation. This little DSO is really letting me down a bit, but I'll press on. There is a certain amount of noise on this signal that is intrinsic to this little DSO. I've made improvements to it, but I still haven't been able to eliminate it. But anyway, going back to this signal, the frequency that it reads is 1.137. Well, I know that's incorrect because this is absolutely spot on at 1 hertz as shown in my grown-up oscilloscope and counter. But what you can see here is the linearity of this hypotenuse. It's very good along here. The voltage that it's reading is 1.11 volts. Well, that's not bad because, as you can see, there is a slight offset at the bottom here of just under 0.1 of a volt, and as I described in the circuit, you can compensate for that, and I adjusted it to as best I could, but obviously I still haven't eliminated it completely. I needed to change the value of that resistor from 390 to probably 470. So the voltage peak here is just over 1 volt, which I described in the circuit. All I wanted to do here was demonstrate the shape of this waveform and its conformity. Other than that, I need to buy a new digital oscilloscope, don't I really?
This is Beamer signing out for now.